This is part 4 of Introduction to LLVM Intermediate Representation for Beginners. Now, I want to return to where we left off previously. So, we know from the previous lesson that insert value instruction can be used to create a struct object in a virtual register. This instruction can take as the starting value either a structure constant or an already existing struct object residing in another virtual register, such as this %obj1. And then it takes a field value to write to that particular field in the struct with its offset. When an already existing object is used as the starting value for another object and an overwriting field value is provided, I32.7, it is only inserted into the new object, which is obj2. The already existing object is unchanged. It just makes a copy of the object used as the starting value, and then it inserts a new field value at a specified index into the newly constructed object. As we can see here, the new field value may be something different, or it may be the same as the former value of the field if you want to keep the original. In order to ascertain that this is the exact behavior, that only the new object is being modified by the second insert value and not the old object, we will perform this experiment. After initializing both objects, we extract each of their values and then we add them all up. Add these %1, %2, %3, %4 into one big sum, and we want to return that and see what that is. So if the original object is modified by this insert value instruction, it would be 2 plus 7 for the object 1 plus 2 plus 7 for the object 2, which is 18. Or if the original object is not modified, the sum would be 2 plus 3 for the original object plus 2 plus 7 for the second object, which would be 14. And if we run this code, we return the sum and we echo what the return value is, we see that it is 14, confirming our experiment that only the new object is being modified here. And this is a very important point. Now, next point here. Now, there is a reason why I use multiple instructions and virtual registers to do the sum here, instead of instruction composition, which is this code being commented out here. It produces this compilation error. In the valid use of function local name, add I32%1. It's complaining about this line right here. So apparently one cannot use virtual register variables as operands to compose instructions, only constant values. However, if I replace the virtual register variables with constants, the code compiles and runs fine. So add the constant 1 to 2, add the constant 3 to 4, and then add up their sum into this sum right here. So the problem occurs when I attempt to use multiple add instructions in instruction composition to add multiple register variables together into one sum. I honestly don't know why variables cannot be used as operands to compose instructions. Is it by design? maybe for enabling data flow optimizations or constant folding or something like that. Is it a limitation of LLVM IR compiler, or is it just a bug? I don't know, but this is just a good thing to keep in mind. Next, we're going to have an example of a struct which contains a pointer to an array and how we can access that. So we have some global variable declaration. So the declaration of a global array or a struct object is first the name, then global keyword, then the data type, and then the value. For the array, its data type is 4x i32, and then the value is just an array constant specifying the initial values that you want to store into the array. And you can specify either an array constant here or zero initializer keyword. The string zero initializer can be used to zero initialize a value to zero of any type, including scalar and aggregate types. It is equivalent to using explicit zero initializers right here. Now, for the struct, this %myStruct is the data type here, which is defined right here. After that is the structure constant, defining the initial values of the structure object. And we can specify that the second element in the struct is initialized as a pointer to the array. So it points to the array. Now this @array here is itself a pointer to an array stored in the memory. It is just a memory location. So now we have an object containing a pointer to the array. Our goal for this exercise is to modify the element at index 2 of the array indirectly using the pointer contained within that object. In the C code, it will be object arrow R bracket 2 assign 50. A trivial exercise in C code, just picking up one line. Usually the same code in LLVM IR is multiple lines long. So first, we get a pointer to an element starting from the base pointer %myStruct pointer at object, offset by 0 myStruct objects indexed into the field 1 of the struct. We get a pointer pointing to the second field in the struct, which is itself a pointer to an array. So the data type here is 4x i32 pointer. So this value that we returned is a pointer to an array, 4x i32 pointer.
Hi, I just have a doubt. Like, can you please repeat how it works?
So this line right here, we are getting a pointer to this element, get element pointer. We are using this myStruct pointer at object as our starting position because the name of an object allocated in the memory is itself a pointer to that object. So we offset by 0 myStruct object, and then we offset by 1 element to get this pointer. And then it is a pointer to whatever is the data type of this field. What is the data type of this field? It is a pointer to array. So %1 is a pointer to array, and then we load just a pointer to an array out of it and store this into this virtual register variable %r.
Okay.
And then because we load this into %r, it contains the same value whatever this field of the object has, so it now points to this same array right here. Yeah, so after that, we use that pointer to an array %r to get a pointer to an element starting from the base pointer to an array, offset by 0 such arrays, indexed into the element at position 2 of that array. Here. So now we have a pointer to this element right here, which is the %2. We can store a number into it. We store the I32 value 50 into the I32 value %2, overwriting the value that was previously at that location. And now it is 50. Now check if that succeeded. So load the value from the array directly using the 4x I32 pointer at array this time. If you notice this line, it is the same as this get element pointer above, but using the at array this time instead of the %r, which also confirms our knowledge that the name of an array in LLVM intermediate representation is actually a pointer to that array. So we're loading whatever happens to be the value in and returning it from the main function. And when we run it, we echo the return value, it's 50. So it confirmed that this indirect access succeeded. Now, reflecting on that, it becomes apparent that in the C code, it does 2 memory accesses and associated address computations to enable these memory accesses. Object arrow R bracket 2 assign 50. One line in C++ code may contain multiple operations. There are 2 in this case. Even more separate operations per line in higher level languages, such as HLSL, GLSL, and Python, for example. Whereas in LLVM, IR, or assembly code, usually a line corresponds to a single instruction, a single atomic operation. So first we have a dereference, a memory access, to get the object arrow R field that is done by these 2 lines right here. Then we have a dereference memory access to get the element of the array, R bracket 2. That is done by these 2 lines right here. The get element pointer instruction dereferences nothing. It only computes the address. In order to do any memory access, you also have to do an address computation. Where in the actual memory is this or that allocated object? So these operations are made explicit in LLVM IR code. This will be more apparent when we look at the next example. Another thing I want to mention, it is apparent on this memory diagram, the at object is stored in the memory directly after the at array because it is declared as a global variable directly below the at array in the source code. The structure type declaration does not take up any space in the memory. It is just an abstract concept for the programmer to make the code more readable. They are similar to type def in C. This saves us from having to type this structure data type over and over again. Maybe that is why names of structure type declarations start with the % rather than the at as for global variables, to imply that they are not actually global variables stored in the memory. They don't occupy any memory location. If structure type definitions would have started with the at sign, that could potentially be a source of confusion, as I see it. Okay, so next slide. we're having the same array, but we are not using this global object. Instead, what we are doing is we are creating an object of my struct type in a virtual register. We are using insert value instruction to create that object. Here we can more clearly see that the first step is getting the pointer to the array out of the object. Now, instead of doing the memory access, we extract the value out of the field 1 of the percent mystruct percent object. And then we get the R out. So these both are in virtual registers. They are not in the memory anymore. And the second step is using that pointer to the array to get the element out, which is the same as we had on the previous slide. Now, the pro of using a virtual register variable to hold the struct object instead is that now there is only one memory access in the second step only. A memory access occurs upon load or store. So if we go back to the previous slide, we have one load and one store, two memory access. However, now, because this struct object is declared in a virtual register, we have only one memory access, which is good because it's more efficient to go to the register than to the memory for getting data. And then at the end, we just print whatever was the resulting value stored into this element. Is the same code that we had in the previous slide, and it is 50, which means that this experiment also succeeded. Now we're going to talk about opaque structure declaration. What is meaning of opaque? Well, transparent exposes the internal details of what fields the structure has. You can see what is inside of it. And opaque hides internal details of what fields a structure has. We just know that there exists a struct type, but we don't know the definition. We don't know what's inside it. We might want to hide the details of a structure's definition from the source code on purpose. For example, designing a high-level interface for the API. The container struct is only used internally in this API. The main function just creates pointers or handles to a container type, and then it calls functions of the API on that pointer to object. The main only pass existing object by pointer, but it can't do anything with it. And it relies on the API for interacting with such objects. Main function just works with that object as an abstract thing. It does not actually know what that object is, and it doesn't need to know. No details of the structure are revealed to the client, so that the client cannot inspect or modify private members inside the structure. Now, having an opaque structure declaration, we can only create pointers to that structure. We cannot create instances of the structure itself, because in order to do that, we would need to know the size of that structure and what fields it has. And the opaque structure declaration contains no information about that. It just has a name. And indeed, it's trying to hide this information. So use opaque structure declarations when the client code only needs to have a pointer to the structure, but it doesn't need to create actual instances of the structure, which is done by the API code. And there are examples of APIs that do this. First, SDL. Objects such as SDL_window are only used in the main function via pointers. The actual objects themselves are created, manipulated, and destroyed only by the SDL API. And two, Clang lib tooling. Many API functions return a pointer to to an AST node living somewhere else in memory, not the actual object itself. The object is only accessed through the pointer. For example, in a callback class, the first step would be getting matched AST nodes out of the match result, which returns a pointer to the matched AST node. It is a common design pattern. Now, having only the opaque structure declaration without the actual structure definition is enough to compile each of these translation units of the client code into the respective bitcode file as the C code, as the LLVM code. And obviously, you would have to link it to a bitcode file containing the definition of the structure and the function, but that is a whole another story. Note that here we are allocating a variable of %container pointer type in the LLVM intermediate representation code. It holds a pointer to the actual %container object, which lives on the API side. Also note that alloca instruction returns a pointer to the allocated stack memory. So this %PTR is actually a pointer to the allocated %container pointer variable. Its data type is %container pointer. Now, you might be thinking, if allocating a variable returns us a pointer to that variable, can we just allocate a %container object and return a %container pointer out that we can then pass into the function? Because the function expects a %container pointer as a parameter, right? That's its signature. But what we are really doing here is allocating an object of type %container, not just a pointer. And in order to do that, you would need to know the exact definition of that structure, which defeats the purpose of an opaque structure declaration. It is the same as creating a container object on the stack in the C code and then passing a pointer to that object into the function. So let's look at the error that the compilers give us. C compiler says variable has incomplete type, struct container X. Because we have forward declaration of struct container on this line. And the LLVM compiler says assembly passed, but does not verify as correct. Cannot allocate unsized type. So it is not the size of that type. So they cannot create an object of type container because they don't even know what that is. So in LLVM intermediate representation, all stack allocated variables are accessed via pointers, which makes such mistakes and misconceptions easy. Think in terms of what is the type of the variable that is actually allocated in the memory. It is a %container. So this pointer does not matter here. Now, next topic, type def in LLVM intermediate representation. We know that we can use type keyword for creating a structure type definition in LLVM IR. For example, we have a type here, and this %mystruct becomes an alias for this structure type that we can then use here in place of the original type. However, type keyword is not only for creating structure types, it can also be used as a generic type def in C, C++ for defining arbitrary data types. I discovered this property by myself. I haven't seen it being mentioned anywhere else, including the LLVM language reference manual. But here it is. We are having a type def for this array, and then I32, and then the float here. So we can rename both existing types as well as aggregates and vectors and any combinations of these types, which is useful alias for large and complicated data types. A type definition can also be based on another type definition, as we see here. And here, renaming a 2D array as HLSL matrix data type name. So here, these type definitions enable us to just allocate an array, and we get a pointer to that array using the pointer to the array %x offset by 0 such arrays indexing into the first array element. So it returns as a pointer to the first element, to the element at index 1 in that array, so the second element, and then just storing an int into the int pointers. See how convenient this is. So, because multiple high-level source programming languages compile into LLVM intermediate representation, I propose that this feature is used for giving the variables the same names of the data types that are used in the high-level language. So int instead of I32 in LLVM IR code. It enables you to have better readability. Next slide. Previously, we have been returning values from the main function and then echoing the return value because we didn't know how to print them to the screen. Now we will learn how to do that using printf. First step is declaring a C string in LLVM IR. We specify a constant, then the C string is actually an array of I8, an array of characters, so we have 13 of them, and then we provide the C and then the string, because it is a C string. And you might be wondering, what are these things right here? These are hexadecimal escape codes. LLVM IR does not accept C++ syntax for specifying special characters. We have to use hexadecimal escape sequences, and each escape sequence is stored as one chart in the memory, not 3. So this is the memory layout for this C string. I have put both the characters and the ASCII values here. We notice that this thing right here has been transformed into ASCII value 10, which is the new line character, and 0, which is the null terminator directly at the end. Now, what if you try to use C++ escape sequences for your C string? You would get a different result than what you expected. So you would have the backslash character at the end of your string, then the end character, then also backslash, then the 0 character, which is different from, it's 48. It is different from the 0, which is the null terminator. So even worse, your string would not be null terminated. So unlike in C, in LLVM, IR does not automatically null terminate your string literals, and you have to explicitly put that in here. Now, for calling printf, we want to provide an exact declaration of any function from the C standard library that we want to link in. The syntax of printf is interesting as it is a variadic function, meaning it takes a variable number and data types of arguments. So the signature printf returns a 32-bit integer. Then it takes a const char pointer, which is just an I8 pointer in LLVM IR, and then we have a ... representing the variadic arguments coming after that. Variadic functions is a whole entire topic that I can create a whole another presentation about, because there's a lot of interesting stuff to it, and if anyone wants, I can definitely create an entire topic specifically dedicated to such functions because they are very interesting, in my opinion at least. So anyway, this hello string is an array of 13 characters, but printf takes in a char pointer or an 8 pointer as a parameter. So we need to get a pointer to the character at index 0 in the C string, much like using an array. We would use this syntax for getting a pointer to the element at index 0 in the array. So this is our char pointer now that we then pass into the printf function for calling. And then when calling the printf function, both the return type and the var arg signature has to be specified. For functions which take a fixed parameters, they just require the return type to be specified, but variadic functions you must explicitly write that they are variadic functions. When we compile and run this program, it prints hello world as expected. And if we echo what is the return type, it's 12. So if successful, printf returns the number of characters printed, excluding the null byte used to end outputs to strings. So that is what being returned here. Now we're going to talk about using format strings in printf. Here, this format string, 22 integer characters. First, it prints out a percent sign. Then it prints a character and unsigned integer, 8-bit integer, then a hexadecimal 32-bit integer, then unsigned 32-bit integer, and then a C string. And then here, this is just a simple C string consisting of the characters mango, null terminated, declaring printf as we saw before. And here we are initializing two variables with initial values. Now, as before, these two are character arrays, but we want to get character pointers out of them. So we need to use getElementPointer to get a pointer to the element at index 0 in each of these character arrays. So this is automatically done in C, C++, but you have to do explicitly in LLVM intermediate representation. And then we call printf function with the first argument being the format pointer to the format string. Now for the percent we don't specify anything, but %8 is for this format specifier, which prints the value as a character, then prints that value as an integer, then it prints this 32-bit number as a hexadecimal value, then it prints it as unsigned, and finally it prints the C string. Now we might also want to use scanf. So first, a brief overview of the code. Once again, we have two strings here. So the signature of scanf is also similar to printf. So we provide that here. And then as previously, we want to get pointers to these two C strings, to the first characters. So that's what we have to these get element pointers. Now I'm allocating a variable on the stack, which returns us a pointer to that 32-bit variable, and here I am printing this print pointer, which is this string, and it says enter an integer. Now, when I'm calling the scanf, I'm providing both the format string and the variable. Now, there are subtle differences in semantics, which type of arguments these functions expect for their format specifiers, even though the syntax is completely identical. So, scanf expects L values, or pointers to memory locations, as arguments, into which is stored input from the console. So it takes a pointer to the L value right here. But printf expects R values as arguments, which are printed to the screen. So in order to print the value of a memory location to the screen, we first have to load it into a virtual register, which is L value to R value conversion, which is done implicitly in C. Only then can we print it. So it prints whatever we enter back out to the terminal. Now finally, we're going to talk about vectors, data type in LLVM intermediate presentation, not to be confused with C++ vectors or math and physics vectors. The closest analogy is CPU vectors. Unlike C++ vectors, LLVM IR vectors are a collection of tightly packed values, more tightly packed than arrays. Like arrays, a vector variable consists of multiple scalar variables. Unlike arrays, the vector is treated as one thing in ALU operations instead of a collection of different things. Vector types are used when multiple primitive data are operated in parallel using a single instruction, which is called SIMD. These SIMD instructions are performed on multiple data values at once, taking one time step to perform the computation on the entire vector instead of one time step for each element in serial code. So we are computing the operation on the vector in big O of 1 versus big O of n. And vectors are placed inside special registers in the CPU, enabling single instruction to be performed on multiple data. Now, these vector registers are actually physical things, having a fixed bit width. It is a good idea to declare your vector variables in LLVM IR code to have the same size as the physical vector registers. For helping the compiler with register allocation, it will put them in the physical vector registers, achieving the optimal possible performance, making sure that the operations are indeed vectorized. So, and unlike structs and arrays, vectors are not considered to be aggregate types according to LLVM language reference. This is the syntax for declaring vector data type. It is similar to an array. How we first declare the data type, then we declare the initial value. In fact, it's just the same as an array, except that we have these less than and greater than signs. So these two signs, less than and greater than, they actually remind me of C++ syntax to create a vector. And zero initializer can be also used to initialize all elements with zeros. Now this get element pointer selects the element at index 0 in the vector and loads it into this virtual register. This get element pointer gets the element at index 1 from this vector pointer and loads it in. And the same for all the elements right here. Now, get element pointer can be used on vectors, but according to the LLVM language reference manual, can get indexed into vector elements. This hasn't always been forcefully disallowed, although it's not recommended. It leads to awkward special cases in the optimizers and fundamental inconsistency in the IR. In the future, it will probably be outright disallowed. So after loading all of these variables, we just print them, we pass them into printf, into the format pointer. This %0 goes into this %i, this %1 goes into this %i, and we see that indeed we are printing all the variables all the values that are in this vector. Okay, so next slide. So instead of using getElementPointer, the correct way to access elements in a vector would be to use specialized instructions. Insert element and extract element. This brings an inconvenience though. This @vec stores a memory location of the globally allocated vector, so it is a pointer to that vector. 4x_i32 pointer at vec1. Hence, it cannot be directly used as an operand for insert element and extract element instructions. The actual vector value has to be loaded from that memory location, from the vector pointer, and stored into here. Only then can you do the extract element to get each element out of it. So here we are getting the element at index 0 from the actual vector value %vec1, as opposed to dealing with a pointer to a vector at vec1. Now, I don't really like this because now we have the duplication of data. One vector is a L value in a globally allocated memory location. Another vector is an R value in a virtual register variable. And both these vectors have the same data. And if the contents of the at vec1 L value change, the contents of the %vec1 R value don't get reflected to update that change. Possibly bad language design, room for bugs to happen if you're not careful. But the important thing is also that at vec1 and %vec1 are different variables. And there is no ambiguity because of LLVM IR naming convention. So if you don't remember, look back to LLVM intermediate representation for beginners presentation part 1 that I did. I talked about that. So once again, I'm printing all these virtual register variables, and indeed we see that this experiment succeeded. Now, suppose we have a 0 initialized vector in the global memory location, and we want to store elements into it. Now the question is how to modify the contents of this @vec1 without using getElementPointer and store on individual elements. This is the code on the left side. Since we cannot modify the L value vector in the memory location directly, we have to load that entire vector into a virtual register for working on it. Then we use the insert element instruction. Insert element instruction inserts a scalar element into a vector at a specified index. First operand of an insert element instruction is a value of a vector type. The second operand is a scalar value whose type must equal the element type of the first operand, and the third operand is an index, indicating at which position to insert the value. The index may be a variable or any integer type, so the result of this instruction is a vector of the same type as the original value, vector value. And its element values are those of the original value, except at this position, where it gets the new value. So we use that for inserting values into the vector. But there's a catch here. Insert element can only insert one element into a vector R value at a time, generating a new vector R value as a result. All R values or virtual register variables are unmodifiable once they have been initialized. So you would need n calls to insert element and n are value copies of the vector in order to fill the entire vector and store the final result back into the memory location, which is what we have here. Maybe it restricts our abilities with that vector because we cannot modify the vector in the virtual register variable. We would have to make a copy in order to modify it. Most likely the vector in the virtual register is treated as a disposable R value, not meant to be kept around for a long time. R values are not meant to be kept around for long anyway, so you can have multiple copies of a variable or a vector available. They are temporaries. I would make a semi-educated guess that the CPU can actually use the same physical register to hold all of these virtual registers if it detects that they are all part of the same dependency chain and are not used anywhere else. The net effect is the same as just modifying one vector, since you only need multiple copies of it in order to overcome a single static assignment property. Overall, it's very similar to working with structs in memory locations versus virtual register variables, which is the topic of next slide. Now, and on the right side, I'm having the code from 2 slides before used to print the elements of the vector at vec1. Instead of just printing the elements of %vec5, I want to directly load every single element from the memory location and print it. I want to ascertain that the store instruction actually works for entire vectors. And when I run it, it prints. So we successfully inserted results into the temporary vectors and then loaded the last temporary vector into the global memory location. But although, as previously mentioned, using get element pointer on vectors in memory is not a good practice. Now, about loading structs into virtual registers, we can use the similar technique for structs as well as vectors. There are 2 ways of modifying a structure object residing in a memory location. First, we can use get element pointer to access individual elements. It can be used with structures because the LLVM language reference manual puts this is because, unlike vectors, structs are considered as aggregate data types, just as arrays. And then we use store into each individual element via the gotten pointer. Now, the second way is creating a R value copy of that struct, or several copies, and then working with that copy. So we are loading the entire struct from the memory into the virtual register, and then using insert value several times, and then storing the resulting struct value back into the memory location. And notice that it's the same as we had in the previous code, except it is a struct, so we are inserting values of different data types directly into it. So insert value and insert element are both used for creating R values of structs and vectors. The only difference is that insert value is used for structs and insert element is used for vectors. But they both have a similar syntax, and they cannot modify existing R values due to single static assignment property, so you have to create multiple copies. Now, the struct R values can also be thought of as temporary copies of the struct object which lives in the memory, used only for performing CPU operations or input-output on the struct. Since the processor only works with R values, it cannot work with L values directly because they are in the RAM. We must first load the struct object from the memory into a virtual register. This can be done in 2 ways. First one is loading the individual elements of the structure one at a time, and second is just loading the entire struct object into a virtual register as we have in this example. Now, I prefer this latter approach because it preserves the semantics of the original program. It might save the program from aggressive optimizations which can be performed considering the variables as being separate ones, potentially transforming your program in ways unexpected. Also, the indices for the get element pointer, when used with a struct, have to be iterally2 data type. Otherwise, this error will occur. If you change them to I64, it would set invalid get element pointer indices. So just keep that in mind. But they can be any other integer data type for arrays or C strings, which are also arrays. So this rule only applies to using get element pointer with the structs. And now, finally, we're going to look at some SIMD instructions. First one of which is shuffle vector. So here I'm having two vectors v1, v2, and I'm initializing them with these values. Now, these two vectors are not R value copies of some L value. They are just like that. I'm just putting them in the virtual registers for brevity in order to explain the concept. And then these vectors are taken as parameters to the shuffle vector. The shuffle vector just puts these two vectors side by side and then selects elements out of both on the vector of indexes, which we supply as the third parameter. So it considers the first vector as being element 0 through 3, and the second vector as being element 4 through 7. And then based on this vector of indexes, it first selects element 0, which is 11, selects element 4, which is the 22, element 1, which is the 33, and element 5, which is the 44. So this is similar to NumPy, if any of you are familiar, how you can have an entire array be an index into another array for the purpose of selecting specific elements out of that array, or we have a vector in this case. So this instruction actually returns a new vector, the elements of which are printed to the console. And if we now extract the elements out of this resultant vector, we print them, we indeed see that it is 1, 1, 2, 2, 3, 3, 4, 4. And now, this last slide, we will cover SIMD ALU operations on vectors. Now, this is where vectors in LLVM intermediate representation really shine. We can perform regular ALU instructions on vector data types, and the operations will be automatically vectorized, meaning the operation will be executed once per vector element. But I think that the ALU instructions are performed in SIMD mode by the processor. So performing a single operation upon all elements of the vector is done at once. As far as I know, all the ALU instructions in a LLVM intermediate representation support vectorization, such as add, sub, div, mul, the arithmetic instructions, and then also casts and conversions. And then I compare and select, and also other instructions as well. They are overloaded to work with vectors, and all these instructions, they only work on actual vector objects, not pointers to vectors, meaning virtual registers only, not L values, only R values, only direct access. That is why I'm having these two vectors into the R values right here. Now, the advantage of vectors over arrays in LLVM IR, as I said previously, is that they make arithmetic on multiple numbers very optimally. Now, suppose we have these two vectors percent v1 and percent v2 representing two sets. We want to get all the elements in percent v1 which are not in percent v2, all the unique elements. So I compare, and E generates a vector of percent I1 data type. Those are the bools, true, where the two corresponding elements are not equal. So it takes them, and is 2 not equal to 4? True. Is 8 not equal to 8? False. Is 5 not equal to 5? False. Is 7 not equal to 9? True. But it does them all at once. So this is the result that we have. But it's a vector of I1. So this zero extension instruction converts the vector of I1 into a vector of I32. And notice that using these type definitions, how convenient it is. We're just zero extending the 4 bools, unique bools, into a vector of 4 int. And then in the next instruction, we multiply that vector of bools by the percent v1 to zero out the common elements and keep only the unique elements. But this small instruction expects that its operand should be the same data type. So vector of 4 I32-bit integers as this percent v1 is. So that's why we need to do the zero extension here. And it just takes this percent v1 multiplied by the unique indices. 2 times 1 is 2, 8 times 0 is 0, 5 times 0 is 0, and 7 times 1 is 7. So we are grabbing only the unique values, and the other values are being zeroed out. We are extracting all the elements and then printing them using printf, and we see 2, 0, 0, 7. Experiment succeeded. So notice how we're extracting the element from the int for data type percent unique value. So with the type defs, it gets rid of all the clutter. So that's it for today.